Hello everyone, welcome back to the course on architectural design of ICs. So, in the last class we have seen the techniques of pipelining and parallel processing and how these two techniques helps to increase the sampling speed or the clock speed of the circuit whenever we have achieved, that means after all the optimization, whether is algorithmic optimization or architectural optimization, whatever logical expression we have got, that means the critical path we cannot cut down by any further optimization. So, at that time there is a that means two techniques are there by which you can increase the speed of the operation of the particular circuit. Okay. So, today and then just prior to that we have learned different adder architecture. So, different adder architecture for different purposes, right. So, here today we will start with multiplier architecture. So, this addition operation, multiplication operation, division, squaring. So, these are the basic operators which are basically used in digital signal processing. Okay. So, then digital signal processing is basically applicable to everywhere, that means whether there is image processing or this wireless communication or any biomedical signal processing, that means everywhere these DSP blocks they are very much used. So, that is why those blocks can be built based on these particular operators. So, now that is why if we, as I said that earlier also I said that if the basic building blocks whenever we are designing, so at that time if we can save. So, whenever multiple copies of that are being used in the particular, that means in the upper block. So, at that time I can save that times of savings in terms of the whether that is power or area. Okay. So, that is why we have to learn this different architecture of this addition operation or this multiplication operation or division operation. Okay. So, today we will see there are different architectures. So, that is why people have tried rigorously, that means to find out the architecture for multiplier or this adder for, so that that will be a high performance design. That means, how we can increase the performance of that particular circuit, that was the major focus in research or that means in useful for any application. Okay. So, now today we will see this multiplier architecture. Okay. So, this is a road map. Multiplication, whenever we will do multiplication, at that time there will be, I think in the basic digital course we have learned there are two type of number system. One is signed representation of the binary number system or any other number system, and there is also unsigned number representation. Okay. So, whenever we will do multiplication, at that time, suppose if I want to multiply 2 into 2 when both are positive, at that time, so I will get 4. But if I want to multiply 2 with minus 2, so at that time the results will be minus 4. So, that means in this case, whenever I have to do this 2 into minus 2, so at that time I have to mention the circuit or I have to design the circuit in such a way, so that it can represent or it can give me the corresponding minus 4 value. Okay. So, that is why there is the multiplication, they are being that means divided into 2, whether that is signed multiplication or unsigned multiplication. Okay. So, in adder also it is useful, that means signed adder and unsigned adders are there. Okay. So, I have not discussed on that particular time, but whenever we will do this multiplication operation. So, at that time I have to consider this. Okay. What is multiplication operation? Multiplication operation is basically repetitive addition operation. What we do in multiplication? In generic multiplication, what we have learned in our, that means during our school times. So, that is nothing but that shift and then add, then shift and then add. So, whenever we are doing this decimal multiplication, so at that time the corresponding position the weight of that is in terms of 10. That means suppose 12. So, 12, how we define 12? 1 and 2. Okay. So, that means the position for the if I just come down to this. So, how we define 12? How we define 12? So, that is 10 plus 2. So, basically this 12 means this is 10 to the power 0th position and this is 10 to the power 1 position. And if I say this is 2, so 112 means what? So, 1 into 10 to the power 2 plus 1 into 10 to the power 1 plus 2 into 10 to the power 0. So, this is 100, this is 10, this is 2. So, total 112. So, the same things in binary if I represent. So, at that time this will be 0 or 1. If I put 0, so at that time the weight becomes this is 2 to the power 2, this is 2 to the power 1, this is 2 to the power 0. So, at that time this value becomes what? 2 to the power 2 into 1 plus 2 to the power 1 into 1 plus 2 to the power 0 into 0. So, that is nothing but 6. Okay. This is unsigned number representation, but in signed number representation there are two formats. What is that? One is sign magnitude, another one is 2's complement format. Okay. So, we will come to that point later, but there are two type of number representation in the negative numbers in binary, that is sign magnitude representation or 2's complement number representation. Okay. So, again if I just so here if you see that in this lecture we will follow this multiplication, then type of multiplication or tree multiplication, then array multiplication, then sign multi-operand addition or this 2's complement multiplication, and then squaring also. Squaring is also nothing but one multiplication operation. Okay. And here whenever we are considering, so at that time all the multiplication operation we are considering that this is what? This is for fixed number, that means no floating point number we are considering. Okay. So, if we have to, that means in some of the DSP algorithms we have to use or we have to, that means perform this float, we have to consider the floating point too. So, at that time how we can do? So, that means at that time multiplier architecture will be different for those type of operations if it is required. Okay. So, that type of multiplication operation or the multiplier architecture also we will see. Okay. So, then this you have to follow, I think I have already mentioned, this is one of the that means best book for computer architecture that is written by B. Parhami. Okay. So, the book name is Computer Architecture, Algorithms and Hardware Design. So, here you will find all these things, that means all the adder architecture, multiplier architecture, all these architectural details are there. So, you can follow this book. Okay. Then what I said, the multipliers they are mostly used for DSP application. Okay. And a variety of multiplier exists that can be chosen based on their performance. That means, so different architecture has been evolved because of different need, whether that is high speed or that is for low power or for that is low area. Okay. And that is why there are the architectures are like serial, then serial, parallel both, then shift and add, then array, then booths multiplication, then Wallace tree multiplication, then Dada multiplication, then hybrid multiplication, then recently that means people have developed this Vedic multiplication. Okay. So, so much of multiplication operation or architectures are there. So, that means in this particular course I cannot, that means as there are plenty of that. I cannot cover all the multiplier architecture. It is better if you just want to, that means the basic, or the, if you know, or if you want to, that means for your research purpose, if you want to consider this multiplier architecture, what will be the newer architecture for, or how you can define. So, we will take one or two case studies where I will show you that how, that means what is the starting point for designing and then implementation of that particular design. That means, my point is that suppose I have to, the multiplication operation everyone knows how we do. The same multiplication operation, whenever we are implementing in hardware, or whenever we are finding the VLSI architecture for that multiplication operation. So, at that time, at what point I have to look, and from looking or from observing that point, how we have to proceed. So, once we have proceed, so at that time, that means finally, how will I map to that particular things on the that means that algorithm. Suppose we have find out one newer algorithm for implementing the multiplication operation, right. So, after finding the algorithm, how then this algorithm can be mapped to the architecture, so that I can get the benefit of speed, power and area. It is not necessarily that means true that all the time I will get all three all together. It is not all, that means all the time it is true, but I will try my level best, or as a designer or as a researcher, I will try my level best to optimize the circuit in terms of these three particular constant. Okay. And apart from that, yesterday's class I have discussed that we are not considering for this accuracy purpose or the resolution purpose. That means, what will be the word length, as I am considering, that means I am working on the fixed point domain. So, at that time, if I consider more number of word length for or for considering the number system. So, at that time I can get more accurate result, but whenever we are that means, and whenever suppose we are considering more number of word length. So, more number of word length means we are basically consuming more power and more area. So, then what will be my choice, optimal choice, so that within that particular word length my results will be satisfactory, as well as my corresponding hardware will also be okay, or that will be also within the limit. Okay. So, that is why we have to do some analysis for that, fixed point analysis or error analysis we have to do whenever we map to the architecture. That is also one part of this, that means algorithm to architecture mapping. Okay. So, that we will see later of this course, that means we will see that as a case studies. So, there we will see, explain, or we will discuss more onto that particular perspective. Okay. So, here, so this is the basic multiplication operation. Suppose I have to multiply x and y, where x is the multiplicand and y is the multiplier. So, in binary, if I represent this x and y, so they both of x will be represented as x0 to x, if I consider x of n bit, y of n bit. So, then x will be represented as x0 to xn minus 1 and y will be represented as y0 to yn minus 1. So, then how we do this multiplication of this particular 2 x dot y? So, that means the bitwise multiplication operation is performed here in binary multiplication. Okay. So, that means now what will happen, this y0 bit of y or this multiplier, the bit of y0, that will be multiplied with each bit of x, and that will be written in this particular in the first row. So, here you see this y0 has been ANDed here, one bit operation, one bit multiplication means nothing but the ANDing operation, right. So, that means this y0 is basically ANDed with x0, then y0 is that means, sorry, here, okay, sorry, here just the opposite thing, that means x0 is the multiplicand and y0 is the multiplier. So, x0 will be multiplied with all the bits of y. Okay. So, then that is why x0 is now multiplied with y0, then x0 is multiplied with y1 up to yn minus 1, x0 has been multiplied and that has been that means reported in the first row. Then what will happen in the next, this x1 will be multiplied, that means the next bit now it will be multiplied with y. But whenever we are, as in the beginning what I said, this numbers are basically what? They are basically weighted. So, that means here this is 2 to the power 0, here it is not 2 to the power 0, it is 2 to the power 1. That means now whenever I am considering x1 bit, that means in binary I have already considering the weight of 2. So, that is why there is 1 bit shift over here. So, that means the weight will start from at this particular stage, it will not start from this particular stage. Okay. So, that is why, because I am doing this 2 to the power 1 by, that means position now, x1 is coming at 2 to the power 1 position. So, that is why this x1 y0 that will come at the 2 to the power 1 position only. Okay, in the same manner now x1 will be multiplied with, that means ANDed with y0 of each bit of y, then x2 will be ANDed with each bit of y and that the position will be what? At this case the position will be 2 to the power 2. So, in this manner I can write all the values of this x up to xn minus 1 I have to write. Okay, actually this row will be in the upper one. Okay. So, after that what I will do, I have to, so these are called as the partial products. So, this particular rows are named as partial products. So, now finally what I have to do, whatever is the, that means the numbers which I am getting after this ANDing operation, so that I have to add and finally I will get the product over here. And another thing is that whenever I am considering, suppose n is 4 here. So, at the time 4 bit, if I multiply it with x of 4 bit with y of 4 bit, so at that time the product will be n plus n, which is 2n. That means, in this case the product will be 8. So, that is why you see there is 2n minus from p0 to, that is p 2n minus 1. Okay. Because this is already, so here if I am considering 4 bit over here and 4 bit over here, so that means this is basically now at this particular case what is happening? This is 2 to the power 3. So, that means this 2 to the power up to 2 to the power 3 it will be shifted. So, that means already I am multiplying with this particular number with what values? So, here this is 2 to the power 0, then 2, then 4, then 8. So, that means already 2 to the power 7, sorry, up to the 7. So, initially I am considering 4 bit over here and then 3 bit I am multiplying with 8 means what? I am left shifting by 3. So, that means initially there was 4 bit for x, now I am just shifting that to additional 3 bit left shift. So, that means now the length becomes what? 7, and where from the another bit will come? As I am doing this bitwise addition operation for finding these products, final products. So, at the final stage there will be the carry out. So, that will be the 8th number of bit. Okay. So, that is why whenever we will multiply with n number of with n. So, at that time it will be n plus n, which is 2n. So, suppose if I am having x of m and y of m. So, at that time what will be the product length? M plus n. Okay. So, if I consider this, So, it says that implementation of multiplication of binary numbers boils down to how to do the additions. Here if I consider 2 bit of A and B of 2 bit, that means 8 bit. So, at that time the multiplication operation will be something like this. So, 8 plus 8 means what? So, total there will be product will be of 16 bit. Okay. Right. So, after that there are, what I said, that there are different type of multiplication operation. Okay. So, the first thing is that initially what we know that shift and then add. Okay. So, that is why this is the serial multiplication operation. Okay. The basic multiplication operation or multiplier architecture, which the not the algorithm, which techniques we have learned during our school times. Okay. So, here you see there is one serial registers, okay, and this x0, this is bitwise serial multiplication. Means what? Serial multiplication, how we can do? We can do it in two ways. Okay. We can, that means all the things, all the bits we have, we can consider together, and then with y0 or y1 we can multiply and then we can add. So, here also the same thing. If you just see, initially what is happening, this x and y, they are being ANDed and they are added with the corresponding output from the this shift register, or this is nothing but the shift register, means that is nothing but the serial register. Okay. So, that means what is happening. So, initially if I go back to the previous slide. So, initially what I have to do, this A0 B0. So, that will come as P0. Okay. So, then in the next A1 B0, that will be multiplied and then that will be added with A0 and B1. That means whenever, that means I will put this x0 and not x and y, the corresponding bit of x and y through a NAND gate, AND gate, and then that will pass through one OR gate if I do this bitwise operation. But here in this case we need addition operation, okay, because we have to generate each of these partial product using AND gate, and then those corresponding partial products, they will be added over here and then they will be passed through one serial registers. Okay. So, this is the, that means operation of the, or this is the serial multiplication architecture. So, this is the very basic of multiplication. So, here what will happen, because as I am considering this, that means serial operation. So, to generate the corresponding partial products, suppose 4 into 4 if I consider, to generate the partial products it needs 16 clock cycle. Then again addition operation of that, then again that will take some time. Okay. So, that means I have to wait, if I consider more number of bits for multiplying. So, at that time my wait time, or the this, if I say that is the total computation time for this multiplication operation, that will be more. Okay. So, that is why this type of architecture is not that much advantageous when you have this critical time requirement. But in this case, what is the advantage? Here, as I am considering the sequential case or the serial multiplication. So, at that time using only one adder I can do that. So, that means the hardware requirement for this type of architecture, that will be lowered. Okay. So, here you see this input sequence of this G1 will be something like this. That means, what I said that this is x and y. So, it will be the sequence will be first x 0 y 0, then x 1 y 0, then x 2 y 0, then x 3 y 0, something like this. For y, the sequence will be like this: y 0 4, then 0, then y 1, then 0, then y 2, then 0, then y 3, then 0 0. For x, what will be the multiple? That means input sequence, that will be x 0, x 1, x 2, x 3, then x 0, x 1, x 2, x 3, then x 0, x 1, x 2, x 3, x 0, x 1, x 2, x 3, something like this. So, this is for what application? If I am multiplying x with y. So, that means now what is happening? By putting this AND gate, that means whenever y 0, then y 0 x 0, y 0 y x 1, y 0 x 2, y 0 x 3. So, that means the first partial product has been generated. Okay. So, then that has been loaded to this particular serial register, then that will come over here and that will be added with this. Okay. So, then again that will be stored in somewhere in this particular register, that will be stored. Okay. And then again that will come, finally that will come, the final results that will come over here. Okay. So, this is the serial multiplication or the bitwise multiplication. Okay. Then we have another architecture, that is serial / parallel architecture. So, serial / parallel architecture is that means, so here this x 0 y 0, x 0 y 0, x 1 y 1, sorry x 1 this x 0 y 2 y 1, x 0 y 2 and x 0 y 3 all together they are ANDed, and they basically produce this. Initially they will produce this, as this basically these blocks are the delay blocks, right. So, initially what will happen, x 0 that will be multiplied with y 0 and that will come over here. So, in this particular case at that time x 0 is not passing over here. So, that means it will be 0, that it will be multiplied with 1. So, it will be 0. So, it will produce S 0. So, 0 over here, 0 over here. So, this S 0 will come here. So, in the next case what will happen, x 0 will be coming to this and x 1 will be coming to this. So, that means at that particular clock phase what will happen, x 0 into y 1 plus x 1 into y 0. So, you see in this particular case what is needed, that P 0 is nothing but this x 0 and y 0 or a 0 and b 0 in this case. In the next what will happen, this a 1 b 0 that will be added with a 0 b 1, right. So, this has been generated using, that means here what is happening, x 0 y 1 plus x 1 into y 0, that is basically happening over here and that is stored here in this particular, and then again all these are zeros. So, then S 1 will come over here. Then in next clock cycle what will happen, in the next clock what will happen, this x 0 will now come over here, x 1 will be here and x 2 will be here. So, that means x 2 y 0, then x 1 y 1 and x 0 y 2. Okay. So, all together they will be added, okay, and then that will come as S 3 over here. So, in this manner all this, that means now S 0 will be shifted, S 2 will come over here. So, if I just go back, so S 0 will be basically, this is nothing but a shift register. Okay. So, initially we have started with S 0. So, in the next S 1 comes, so S 0 shifted over here, S 1 fills with there. Then in the next S 2 over here, S 1 over here, S 0 over here. Then in the next S 0 over here, S 1 over here, S 2 over here, S 3 over here. Then again in the next S 0 will come, S 1, S 2, S 3, S 4. In this manner, so at the very last So, S0 will come over here and S7 will fill here. So, after that I will get the corresponding output of 4-bit multiplication operation. So, at that time what will happen, the corresponding the x0, what will be the input sequence of x0, that will be x0, x1, x2, x3, then 0, 0, 0, 0. So, that is the input sequence for x0 for this particular case. So, this is the combination of serial as well as parallel. Okay. So, that means this parallelly basically I am computing this partial products. Okay. Then I am doing the addition in serial manner. So, that is why this is serial and with combined of parallel operation. Okay. So, then what I said that there is this shift and add multiplier. These are the basic multiplier. Okay. So, again we will see this shift and add multiplier along with other multiplier architecture in the next class, and thank you for today's.